Sidhanth, Mohanty.
Yeah, thank you for the introduction, Ryan, and thanks to all the organizers for the invitation to speak here. So let me remind you of what I'm going to prove. So A is going to be the adjacency matrix of an Erdős-Renyi graph, where the S probabilities are D over N, and you should think of D as being a constant. And we're going to use A bar to denote the centered adjacency matrix. And our goal is going to be to show that if X is any positive semi-definite matrix with ones on the diagonals, then with high probability, the value of the Lth non-backtracking part of the centered adjacency matrix is dot product with X is at most the square root D to the L quantity. So okay, strictly speaking, we're going to show it's at most 1 plus epsilon to the L square D to the L for large enough constant L where L depends on epsilon. But from now on, I'm just going to use less than approximately equal to hide this 1 plus epsilon to the N.
Hey, can I ask a question? I'm sorry to jump in so early in your talk, but this is actually a question sort of from the combination of the two talks. So this SDP doesn't have any new constraints on X. It's what's different from the kind of good old fashioned SDP is that you're taking the inner product with this backtracking length L power instead of the adjacency matrix. So is this, forgive me, but is this somehow dual to the idea of taking a more complicated SDP with more constraints that Jess was talking about? I guess there, right, this is a simple SDP with a different inner product thing as opposed to an SDP with more constraints. Am I missing something obvious here?
Yeah, I guess I'm not really sure what you mean by dual.
I think that
yeah,
because I had the same confusion as Chris, but all of these are constraints, right?
Yeah, all these are constraints.
One for each this inequality, AL dot X less than square root of D to the L for each L. Right?
Right. So not that I can jump in. I think I could have set this up better in mind. The point is that this little result, or very large result, as it turns out, that's not approved, is just showing that some particular constraint is violated in the SDP with lots of constraints that I mentioned in the prior talk.
Right. So actually, for the planet model, if you're above the KS threshold, then this A.L.X, where X is a planted solution, is going to be way larger than square root of D to the L. And here we are showing that in the null model, it cannot exceed square root of D to the L. And hence, the null model can never hope to satisfy this particular constraint. Okay, yeah, so I guess
perhaps you should state that the SDP is just check the feasibility of all of these constraints for each L.
Right? Yeah, that's exactly right.
May I also chime in? Prasad says, sorry. Prasad Raghavendra says as a comment, at degree 2, local statistics reduces to non-backtracking walks, since the only local statistics with 2 labeled vertices are non-backtracking walks.
Right. Okay, yeah, so I guess we wanted to prove this bound on the SDP value of square root D to the L. And before I move on, I just want to point out that several of these ideas actually do come from, are inspired by previous papers, namely once by Bourdonov, Lalage, Massoulier, a paper by Fan Montnari, and also some joint work with Ryan O'Donnell and Pedro Paredes. But the main technical challenge here is somehow getting the statement to work for L being a large constant, whereas these previous works can only get such a statement to work for L being something like log squared n. And as a first attempt, you could make the observation that actually the Lth non-backtracking power, the operator norm, the Lth non-backtracking power, is actually an upper bound on the SDP value. And one could hope to prove the bound that we want by bounding the operator norm. But actually, trying to do this directly fails. And it actually fails for a fairly simple reason. Because with high probability, an Erdős-Renyi graph is actually going to have vertices of degree roughly log n, which automatically gives the matrix a super constant eigenvalue. But actually, this bound that we want to show, square root D to the L, is a constant. But actually, the reason for which this fails also gives us a simple fix. So one thing we can notice is that a typical vertex has degree d, or more generally, if you look in the distance t neighborhood of a typical vertex, you're going to see roughly d to the power t neighbors. And there's only going to be like a very small fraction of vertices whose balls exceed this d to the t number by a lot. And what we're going to do is we're going to delete the small number of vertices from the graph. By the way, notice that this is just something for the analysis. So let me define M to be the Lth non-backtracking power of the adjacency matrix of the graph where certain bad vertices will be deleted. But bad vertices are the ones which participate in short cycles, and also the ones that have large distance t neighborhoods. And actually, since we have this particular constraint on the SDP that the diagonal entries are all equal to 1, we can actually show that deletion of vertices does not really influence the SDP value by much. And it turns out this new matrix M is indeed spectrally bounded by square root d to the L. So now we're going to jump into the proof of bounding the operator of M, but I'm going to pause for a second to see if there are questions.
Well, since you ask, so deleting vertices on short cycles feels a little bit like up to some point using self-avoiding random walks rather than just non-backtracking, or if you like, non-backtracking with a bit more memory, right? Like you may not visit any of the past 3 or 4 or 5 places you've been. So
right.
I'm just wondering if there's anything to be gained by that kind of power of the adjacency matrix, since non-backtracking sort of has memory 1.
Yeah, so I guess I'm actually still not sure of how to make the proof go through if we use self-avoiding walks, for reasons that I will address actually on the next slide. Right, so our approach for bounding the operator of M is actually to start by bounding its kth moment by some number c. And once we have a bound on the kth moment of c, if k is like a large enough number, then we actually have a bound on the operator norm that holds with high probability of c to the power 1 over k. And the way we're going to try to bound the kth moment of M, of the operator of M, is to notice that when we choose k to be an even number, the operator of M is actually bounded by the trace of the kth power of M. And actually, the hope is that the expected trace of the kth power is at most square root d to the L, whole thing to the power k. So is what we want. So we can get the desired operator norm bound on M. And Chris, I'll get you a question very soon. So our first natural goal is actually to try and understand what the trace of the kth power of M actually is. And if you do a little bit of combinatorics, you will see that the trace of M to the k is like a sum over a huge variety of walks. And in the sum over a huge variety of walks, the summand is actually an appropriate weight of a certain walk. And now let's understand what this huge collection of walks is. So actually recall that M was the Lth non-backtracking power of a certain centered adjacency matrix. So trace of M to the k is actually counting, or is actually summing over closed walks, which have length k times L. And these closed walks have a very special structure. In particular, they're composed of k non-backtracking segments, each of which have length exactly equal to L. So okay, now let me quickly address Chris's question. So if we instead use self-avoiding walks instead of non-backtracking walks, then we'd be looking over walks where there's case self-avoiding segments of length L each. But as you pass from one self-avoiding segment to another, you could still encounter short cycles, and this could cause problems in our analysis. So okay, I'm gonna momentarily pause here too to see if people have any more questions. Okay, so now let me keep going. So this particular trace of m to the k quantity, it's like this crazy sum over all walks and looks super daunting. So actually, fortunately, I'm not going to make any of you actually think about this. Let me just say that there's a lot of song and dance that one needs to go through before you get from this point to something interesting. So I'm going to perform a sleight of hand and fast forward to where the next interesting thing happens. And here, by waving my hands a little bit, I'm going to say that this trace of m to the k, which is like a sum over walks, weight of w, is dominated by a very small number of walks with very nice structure. In particular, it's dominated by walks which are even. That is, every edge is walked on an even number of times. And also, these walks have the property that they have almost no cycles. They're very close to tree, and all the cycles on them are also very long. And the first interesting combinatorial question in trying to account for these walks is to count walks on a tree. So let me set up a clean combinatorial question. So you have a DRE tree. It's rooted at this vertex, which has been labeled as V. And we want to count the total number of closed walks that start at V, end at V. These closed walks need to have length KL, and they need to have a special structure that they're composed of K length L non-backtracking segments. And recall that we'd be happy if the bound we could get on the number of such walks is square root of d to the L. And the way we are going to bound the number of closed walks is via an encoding argument. So if you give me any walk on this tree, and if I can compress the description of this walk to log of some number c bits, then I've actually bounded the total number of walks by c. So in particular, I'll have to give you an encoding of closed walks of the special structure in the tree using KL over 2 times log d bits. Now, the first observation that goes into this particular encoding is that, okay, so first let me define what an up step is and what a down step is. So notice that every step in this walk either moves away from the root or moves closer to the root. So if a step moves closer to the root, you can think of it as climbing the tree, and we call it an up step. And if it moves away from the root, we can think of it as descending down the tree, and we can call that a down step. And because you have to start at V and end at V, the number of up steps is actually equal to the number of down steps. In particular, half the steps are up and half the steps are down. Now, here's the second observation. And this is where we're going to use like the special structure of the walk of being composed of K non-backtracking segments, which each have length L. So in one of these length L non-backtracking segments, I claim the structure is always I move S steps up and L minus S steps down, where S is possibly 0. And the reason for this kind of structure is if I take a down step, the only moves I can make in non-backtracking fashion are also down steps. So this actually really constrains what a segment can look like. And this is going to inform the following way to actually encode a walk. You give me a walk W, And then what I'm going to do is in each segment, I'm going to see what this number S is, like how many up steps are there. It's going to be a number between 0 and L. So I'm going to use log L bits to write down how many up steps are taken per segment. So for example, maybe this part of the encoding just looks like 0 up, 2 up, 3 up, 5 up, and so on. And and notice that this takes log L bits per segment, so that accounts for k times log L bits. So another thing I want to point out is if I tell you that you're taking an up step, or if you know that you're taking an up step, I don't even need to tell you where you're going because every vertex has a unique parent. But if you're taking a down step, I do need to tell you where you're going. In particular, I need to tell you which of your D children you're going to. So encoding each down step takes log D bits. And since half the steps of the KL steps are down, this accounts for log D times KL over 2. And actually, this log D times KL over 2 is like the number of bits we wanted, but we have like a bit of bonus. Okay, but the surplus number of bits ends up being something pretty insignificant. That you're paying only log L over L per up step. And that's the source of your savings. So this establishes how one counts walks in a DRE tree. So now I'm going to move on to an overview of how one actually counts walks that have some small number of cycles in them. But before that, I'm again going to pause for a second to see if there are any questions. Okay, so let me keep going. So we actually now care about understanding walks on shapes that may contain some cycles. So in particular, you could have some graph that looks like the one on the left. And there's some vertex V, and we want to count V to V closed walks, which satisfy the same set of conditions that we discussed earlier. But this is no longer free. So actually, the strategy at this point, and I would say this is like roughly where new ideas start coming in and we depart from past work, is to identify a spanning tree as well as a set of excess edges, namely the edges which are not in the spanning tree. And now once we have a decomposition of the shape into a spanning tree plus excess edges, we note that any walk breaks down into an alternating fashion where there's a stretch of the walk that's on the tree, followed by a stretch that's on the excess edges, followed by a stretch on the tree, and so on. And now the way we're going to encode such a walk is by actually encoding the tree segments in an almost identical way to what was described earlier. So note that actually the tree segments are no longer closed walks because really they go from one endpoint of an excess edge to another endpoint of an excess edge, and these two endpoints need not be the same vertex. But I guess it's suffice to say that an almost identical idea works for encoding these segments of the tree walk. And actually, the way we're going to encode excess steps is also rather naive. For each excess step that appears, we're simply going to list, we're just going to make this big list of excess edges in the order in which they appear in the walk. So I just like wrote an example encoding at the bottom. But actually, if the number of steps on excess edges is too big, we could run into trouble because this list of excess steps could be really large. So we can't just choose any spanning tree. We need to be clever about which spanning tree we choose. And I guess a rather natural choice of which spanning tree to use would be you take the shape and then you weigh every edge by the number of times it appears in the walk and choose the maximum spanning tree according to these edge weights. So this choice definitely minimizes the number of excess steps that one takes. It minimizes the list of the excess step encoding. However, it's still not actually clear that the list you get is short enough in length. And yeah, I won't have time to get into how one actually proves that this list of excess edges is very small, but it's actually a part of the proof that I really like, and it involves like some nice tools from combinatorics, such as the Moore bound for irregular graphs, as well as properties of a linear programming relaxation of finding maximum spanning tree. And this actually ends the technical part of my talk. And now I'm just going to discuss 3 future directions. And then we'll have time for questions. So the most natural next question is the following. This local statistics thing gives us an algorithm for the distinguishing problem. It's natural to ask whether the search problem could be solved. So okay, let me be a bit more specific when I say search problem. You want to, so the basic version of search problems, you want to recover, say, in the 2 communities, you want to recover the 2 communities better than random guessing would. But actually, there's a more nuanced question here, which is for a given 2 community block model with certain setting parameters, there is an optimal possible recovery that you can perform information theoretically. And there's a paper of Mosul, Niemann, and Sly, which does this, but not right down to the KS threshold. They do it at like some factor, maybe 10 above the KS threshold. So one question is whether rounding the local statistics SGP could solve this problem right down to the KS threshold. And yeah, this is a problem that probably needs like new ideas and could be very interesting. Another direction is, well, we illustrated how to apply this SCP to certain hypothesis, to the hypothesis testing question of community direction, but one could ask whether it could be applied to other natural questions, such as finding planet spikes in Wigner matrices or planet solutions in random constraint satisfaction problems. And here's another direction that would be to try to apply these ideas beyond the realm of Bayesian inference. In particular, let's say you want to determine moments of Gibbs distributions for your favorite problem. Like let's say you had a deregular graph and you wanted to know what the moments of the uniform distribution on 2D colorings were. And there are algorithms for sampling from Gibbs distributions in some cases using Glauber dynamics or more generally some form of Markov chain Monte Carlo. But the question is, can the local statistics SGP be used to give deterministic algorithms in these settings? And I think with that, I'm done.
Okay, let's thank Jess and Sidhanth together. See if I can pipe in some applause. Should have faded that out. Okay, great. So now I guess Jess and Sidhanth can potentially even team up on answers to questions that you may all have, for which we still have plenty of time.
I just want to check with Chris whether I answered his question about self-avoiding blocks.
My question was a little vague, so yes, you did. I was just trying to connect it with, I guess, Masulia's positive result from some years ago about using the matrix that counted self-avoiding walks up to a certain length. I wonder if one of the things you've done is find a simpler proof of that somehow, sort of, kind of.
So some of the point is you have to delete all the vertices that appear in short cycles.
Yeah, so okay, one thing that I realized we didn't really communicate is that the reason we need to do this like whole deletion procedure is because we were also actually shooting for this additional robustness property in our algorithm, which is if an adversary deletes like delta n or deletes or inserts delta n edges, where delta is a sufficiently small constant, we still wanted to solve the distinguishing problem sufficiently close to KS threshold. And that's why we needed to get the proof to work for like constant L. Otherwise, the old machinery does work without any like deleting vertices and short cycles or deleting high degree vertices. And you just have to make L like log n squared.
Sorry, but does this mean you don't get a polynomial time algorithm?
You do get a polynomial time algorithm because I guess these non-backtracking powers can be computed efficiently.
Also, there's a comment from Prasad Raghavendra in the audience. He says, future direction number 4, show lower bounds for the number of rounds of local statistics STP hierarchy below the KS threshold. This will be evidence towards proving a computational phase transition where the problem can be solved by degree 2 local statistics above KS threshold and no constant degree local statistics STP below the KS threshold. Yeah, I think maybe Jess might have implicitly said that question in her talk, but yes, this is also a great open direction, I think.
Yeah, thanks, Prasad. I meant to add it, but forgot about it.
Can I ask a question about this robustness guarantee?
Sure,
so I think there was a paper by Ankur and Alex and Amelia several years ago now, which showed some lower bounds about also having to do with robustness, and I don't remember exactly what the formulation of their result was. Can you say what is the relationship between these things and whether you're...
Yeah, so actually in that paper, what they showed is that depending on the, depending on what the adversary, depending on the number of insertions and deletions that the adversary can make, the KS threshold actually shifts up. And they gave an algorithm that was robust at twice the KS threshold. But I guess ours was like a more fine-grained robustness theorem where we're able to say we can be robust to delta and edge insertion deletions, epsilon close to the threshold, where epsilon depends on delta. And okay, one thing that I do want to point out is in their paper, they actually considered a different noise model as well, where the adversary is monotone. The adversary could add as many edges as they wanted between communities and subtract as many edges as possible within communities, or maybe the opposite. But okay, we only allow like bounded numbers. And I guess trying to see if like these ideas can be used to get better settings in the other noise model is also a cool direction.
Thanks.
Yeah, I don't know if everybody saw, but in the chat, Alex Wine said different form of robustness. We allowed an arbitrary number of monotone changes.
Yeah, that was actually the model I just mentioned.
Yeah. Let's see. Some more questions. Do you have like, go ahead, Chris.
So I think I'm just saying back what Sidhanth just said. I just want to understand. So it could be that actually counting self-avoiding walks up to a certain length could be somewhat more powerful than kind of that level of using non-backtracking walks. But on the other hand, doing that for lengths larger than log n is computationally expensive for self-avoiding walks, whereas for non-backtracking walks, there's a linear recurrence that allows you to do it in polynomial time. So that's kind of, yeah, that's sort of, okay, anyway, that's interesting.
Yeah, I was gonna ask, can you prove like lower bounds for this local statistics SDP for like any kind of like toy problem? Or like easier problem?
Right. I guess if the SOS degrees too, we showed that if you make your local statistics degree any large enough constant, you can't beat the KS threshold.
In the case of deregular graphs and the regular
and also the block model.
Right.
But I guess Yeah, I guess we don't know any lower bounds where you're allowed to up the SOS degree.
Right. So I think analogous to SOS, where there's kind of this quadratic barrier where lots of nice things happen.
Yeah, though I think I should mention the Barack Hopkins, Kothari, Porichin, Moitra, Kellner paper for like sum squares lower bound for planetary.
Nice.
It also gives a local statistics lower bound. Though this like presaged local statistics, so they don't like say it that way.
I see.
Or I think in general, pseudo calibration based approaches probably should give local statistics lower bounds. That's like the sense I have.
Is the same true for the Sherrington-Kirkpatrick lower bounds?
Yeah. I guess it's true for, strictly speaking, it's true for the planet Boolean vector lower bound. For the SK lower bounds comes from like another layer of reduction. So, like you'd have to talk about what planet model you're using if you're asking about local statistics SK lower bound.
Okay. Thanks.
Actually, at some point, wouldn't you expect local statistics to do something interesting in Sherrington-Kirkpatrick because of Andrea's algorithm?
So I guess we also need to be clear about which computational problem we are talking about. So if you're talking about refutation, it's not clear it should, but maybe for search, presumably.
Yeah, because Andrea's thing is talking about the random problem where you don't have some planted structure. So that's actually okay. So you need to define something.
Yeah, but presumably
make something well defined,
like a solution that matches moments of the Gibbs distribution, then maybe at some number of levels, something interesting could happen.
This is going back a little bit in time, but Prasad also made a comment addressing Chris's question. He said that the number of short cycles of length less than log n is small, and deleting or add them would not change the statistics in this model, so the SDP is not sensitive to it.
I guess this is a much more naive question, but sort of for the community detection type questions, I can understand that these are the sort of statistics that you look at are related to sort of the local structures in the graphs, and you look at non-backtracking walks and so on and so forth, right? But sort of to one of the questions that Sidhanth had on its slide, leading to, for example, spiked Wigner matrices and stuff, you would look at sort of the same length k non-backtracking walks possibly on the Wigner matrix, but in some sense they are not so local, right? So I guess I'm wondering sort of in other problems, how local you expect things to be and what that would mean, I guess, if you have some understanding of that.
Right, so I guess one thing to keep in mind is that the local statistics SDP is looking at more than just the local structures in the graph, because it's also trying to search for like a planted spike at the same time.
Sure.
So presumably, even in something like spiked Wigner, if I take two vertices and I look at all length L non-backtracking walks between these two vertices, let's say multiply the edge weights, I think I would expect that to be correlated with the product of.
Oh yeah, no, I'm sure they're
correlated.
I'm saying that maybe they are not so local in this sense, but yeah, I mean, I understand. Sure.
Okay, do we have more questions for Sidhanth and Jess?
Yeah, how does the running time depend on your proximity to the KS threshold?
Right, it's actually a reasonably good dependence, because the SOS degree only needs to be 2, and the only thing that's increasing is the number of constraints. And the number of constraints just becomes like a large constant. And computing these matrices takes like, computing the mth matrix takes order m matrix multiplication.
Oh, cool.
So it actually stays like an SDP solve plus like matrix multiplication solve time.
Great. Okay, so we have another talk in 2 minutes. So we'll all take a little teeny break. And if Ahmed wants to set up, that'd be great. I think he should be able to control the screen share.